So tonight, what are we talking about tonight? We're talking about hidden figures, hidden elements, things you may not realize, things that you kind of can overlook. When you look at a watch today, what are the things that jump out at you right away? The case, the dial, the strap, the hands, things that are obvious that you notice right away. But there's a lot more to it than that. And that's what we're going to dive into tonight. So I'm very pleased to welcome my good friend, editor-in-chief of Le Quai de Horloge, coming to us all the way from Sun Valley, Idaho. Please join me in welcoming Mr. Jeffrey Kingston.
Thank you, Nick. Good evening, everybody. Glad to be back in New York, and glad to be in New York, particularly since it feels like we're getting back to normal again, and hopefully it'll be something that will endure for us. So I'm going to start with having you think about some things. What aspects of a watch bring value to the watch? What do we really celebrate? There are a lot of obvious kinds of candidates that you see. For example, we see complications, we see features, great finishing flourishes, thinness. I could go on and on. There are a whole host of different elements that probably come to your attention when you look at a great watch. These, I think, are all pretty obvious. You see them with the watch in your hand. As a matter of fact, what was interesting, earlier this evening, I was looking at some emails that I get on various watches on the market with some of you, and we were remarking about how it seems there's one other quality right now that has entered into the equation that has nothing whatever to do with substance, and that is scarcity. People seem to be also valuing watches that they can't get, and the more they can't get them, the more they really want them. But we'll put that all aside. I want to go a little bit deeper now. I'm going to try and illuminate just 5 areas that I don't really see people talking about a great deal. In fact, I can guarantee you that are a couple of elements, or 3 at least, where I'm fairly sure maybe none of you have ever talked about it, thought about it, debated it, or otherwise evaluated it. And hopefully I can broaden your mind so that we will start thinking about some other elements that bring incredible value to the watch. The 5 topics I'm going to focus on tonight are inertial regulation, silicon hairsprings, copper beryllium wheels, multiple mainspring barrels, and a secure calendar mechanism. Now, I call these the hidden figures, and I think it's a nod toward Aldous Hodge, who is a trustee of the society. I think all of you know of his profile in the watch world, and I've been very happy to have moderated a panel here in New York with Aldous, and also even one in Dubai. He's a good friend, brilliant actor. He was in the movie called Hidden Figures. So I grabbed the name because the theme of the movie is really something that overlaps with what I'm going to talk about tonight. The movie talks about Black women who were hired by NASA to do the calculations for the early part of the space program. People didn't trust computers. In fact, the astronauts, even though they had a computer, as the story goes, wouldn't rely on what the computer said without these women working in the background who had done the calculations by hand so that they had some assurance they would be right. These women were not talked about, were not publicized, they were in the background, they were essential to the early days of the space program. They were the hidden figures, that's what the movie is all about, and I think that describes perfectly what we're going to talk about tonight. So there was actually can we just leave that on just low then? There was an event that took place that I consider sort of the first hidden figure. It goes back to 1790. It involves Abraham Louis Breguet. So here's the scene. He is in the Salon of Talleyrand. actually, I should give all the names because French don't like just one name. They like to have 4 names. So Charles Maurice Talleyrand Périgord. In the salon, Breguet has debuted his invention of the parachute anti-shock, which protects the balance staff from breaking. Very important watchmaking invention, one of his many inventions, as a matter of fact. To demonstrate it to the crowd that was assembled, obviously he was thinking of them as clients, he flings the watch to the ground and the watch doesn't break. The crowd is horrified at what he has done, but the watch still runs. He's demonstrated a hidden figure, something inside the watch people didn't know about, people didn't appreciate, but he showed them what it really brought to the watch. I consider that one of the first real hidden figures in watchmaking. So here's how I think about it. It's kind of the theme for what we're going to talk about. Does it deliver value? Does it really represent real substance in the watch? And 2, can it deliver value without shouting about itself? So that's kind of what the theme will be for tonight. So our first topic is going to be regulation. Now, we really see 2 main systems. There can be others because we have some different kinds of escapements and things are around. But in general, for modern watches, we have 2, inertial regulation and Raquette regulation. And I hope what I can do tonight is illuminate further the advantages of inertial regulation and perhaps highlight some of the reasons why it is superior to a Raquette. So I've got on the screen now an illustration of Raquette regulation. We really, you can see of course, the hairspring here. We really have 2 main components that we're going to be looking at. The stud here, or the French word piton, where the end of the hairspring is attached firmly. Okay. The idea is this Raquette, which is labeled A, can be moved back and forth by the watchmaker, which will change the effective length of the hairspring. And that is how the rate is being adjusted. Okay. The part of the hairspring that is between the Raquette and the stud is inactive. It's taking no role at all in the running of the watch. Basically, the Raquette is determining the length of the hairspring and the part of the hairspring that is going to be active for the watch. So I think immediately you can see one issue with this particular system. And that is the regulation is a matter of trial and error. It is a manipulation of the Raquette, observing the watch on a timing machine and basically seeing what did I get from that. And then going back and forth until the watchmaker is satisfied that the watch is running and regulated satisfactorily. So trial and error is really the order of the day. Now, let's look at some other dimensions of a Raquette. And I've got some illustrations here. This illustration, of course, is exactly what you saw from that picture of the watch. Going to bore in a little bit more on the Raquette and what happens as the hairspring goes through the Raquette. This blown up picture, I think, shows it quite well. If you study it, you can see a problem. Basically, you have the hairspring now passing between what amounts to 2 posts. Automatically, there has to be a degree of movement that is possible of the hairspring between those 2 fixtures on either side. Can't be avoided because we're going to be moving the Raquette back and forth anyway to regulate the watch. And that movement can be side to side, it can be up and down. And depending upon the gods, you're going to get changes in rate, and you can get changes from position because of that. It's small, but it's still there, freedom of movement of the Raquette. Now, what did I just do? I think I hit that button. Here we go. So let's now contrast that with inertial regulation. Now, the first thing you're going to see when you look at this picture is that you don't see a Raquette anywhere. All you see is the fixed stud, which is here, no raquette. The regulation is being done by the 4 gold screws around the perimeter of the balance wheel. The principle is trivially easy, and it's actually part of our own experiences. If you've ever seen an Olympic ice skater starting off, with arms outstretched with a relatively slow spin, and as they pull the arms in, the inertia decreases and the spin speeds up. And that's exactly the idea of inertial regulation. By moving the screws in and out together, you have to keep the balance, of course, balanced. You don't want to turn one screw on one side and not the one on the other side. You have to do both. You regulate the watch. I think you'll see, I've got another picture here. This is actually a slightly different balance wheel. This is one that the Blancpain uses in some of its watches. The idea of this one is that the screws still function in the same way for regulating the watch, but by moving them slightly inboard, the idea is that there's a little bit less air resistance. And if you're fitting it, for example, inside a tourbillon, you could make the balance wheel bigger because the screws are not protruding outwards toward the carriage. So let's keep hitting this one button. Let's go over the inertial regulation advantages. The first one is it's very precise. When movements are designed now, the movement designers, the term that's used in the industry is constructors. I always find that kind of interesting because the constructors don't construct, they design, but that's just between me and them. The constructors or designers can actually calculate now how many degrees of turn of the screw will correspond to what kind of change in the running rate of the watch. Very precise. The trial and error element is greatly diminished. Of course, you'll verify it on the machine, but at least you have a target and you know where you're going to go when you do it. There is another important element, and this is something that cannot be overstated. With a raquette, you have the movable arm that is susceptible to movement in the event of shock. I would say it is essentially impossible for the regulation screw's position to be moved at all if the watch is subjected to shock. They are screwed into something. So you don't really expect that there could be any force vector that would make that screw turn if the watch is subjected to a shock. So you get much better reliability and robustness from an inertial regulation. Now, what I'm going to show you next is actually part of a training video that Blancpain uses, which shows how you regulate the watch. Now, think about something for a moment. When you do the final regulation, you're doing it with the movement in the watch, the movement fully assembled. So how do you access the screws to make these fine adjustments? What exactly is the technique? One of the things that really impressed me is they developed what looks like an incredibly simple, obvious tool to give to their watchmakers to access the screw and then be able to measure how many degrees they have moved the screw. When you see this in the film, you will say, of course. But it was entirely obvious you would do it this way, but it wasn't obvious. There is no tool on the market available for watchmakers that does this. This was developed entirely by Blancpain, by its tool making department. So let's take a look at the regulation process and you'll see how a watchmaker does it. We should have music, but they don't think of that for this. So here is the tool with one end that can mate with the screw. And as you turn it, you can read the number of degrees of rotation that you've accomplished on the side, that plastic barrel. good reminder to the watchmaker, keep the balance wheel balanced. Now here we're actually going to see the adjustment of one of the screws. Holding the balance wheel, because we're going to have the tip of the tool mate with the screw. And you can't quite see, but on the barrel, you could measure how many degrees you turned the screw. Our next topic is silicon hairsprings. Now, what did I do again? Did I keep hitting that one little button? So I want to calibrate our discussion of silicon for a moment. It's this. It is a marvelous material. But the thing you always want to keep in mind is it being used in a way that is compatible with, keeps the spirit of traditional watchmaking? Are the gestures the same? Do the watchmakers work in a similar kind of way? The way I look at it is silicon is a material that sits in the evolution of hairsprings, where we have had generations of different metallic alloys come along, each one presumably a little bit better than the ones from the past and so forth. In that evolution, we come to silicon. And the good thing about a silicon hairspring is all of the traditional ways in which you work with the watch are more or less preserved. And that is really important. We have seen silicon show up in some watches where, I won't name names, you are hard pressed to say that it really resembles a mechanical watch as we know them and as we love them. This is just kind of an illustration that you can manipulate the hairspring in the same way you would manipulate a metallic Nivarox hairspring. So what are the advantages of silicon? I've said it's a better material. It sits in the evolution of materials getting better than the ones that preceded. The one that is mentioned the most is its resistance to magnetism. We'll show the problem of a metallic hairspring with this next video. This is a regular metallic hairspring, and if you've paid attention to what I've talked about up till now, you'll see a raquette in this particular arrangement. A magnet is going to be moved over the hairspring, and take a look at what happens to the hairspring, and take a look also at the balance wheel, which even moves. That is why magnetism is an enemy of a metallic hairspring. Now, there are two elements which don't come out of that video. What you saw was one element. That element was that the presence of the magnet and the magnetic field at that moment magnetized parts of the hairspring. So instead of having a spiral, you had little miniature magnets in parts of the spiral, some parts attracting the other parts, some parts repelling the other parts. And so you saw the spiral deform in the presence of a magnetic field. That's one element. There's another element that's more insidious, which is if the magnetic field is strong enough, the hairspring will stay magnetized after that magnetic field is removed, residual magnetism. So you have both. What's going to happen to the watch when it's in the field, and will that persist when it's taken out of the magnetic field? That wouldn't happen with any kind of a magnetic field that we would ordinarily expose our watches to. That would include even wearing your watch, which I would never imagine anybody would, in an MRI machine, for example. In fact, the last time I had an MRI, I wanted my watch in the next room. I thought, well, who takes a chance? So magnetic resistance is an important characteristic, but there are some more. Now, this is a slide that I used in my talk about tourbillons for Breguet, but it illustrates a very important point, and it probably is one illustration that shows it more clearly than any I know. With a traditional metallic hairspring, basically you're making a wire. and forming it into the form that we know. But that wire is going to be uniform along its length. There isn't really an easy way in which you can engineer stiffness in some parts and flexibility in other parts. Just not really possible. With silicon, that becomes entirely possible. And you see here with this hairspring, which comes from the Breguet chronometrie, that it's actually a double hairspring. There are parts that are very, very stiff. You can see it looks even like a bridge. Other parts would be more flexible. So the watch designers, the movement designers, can engineer where they want the hairspring flex to start and how it will be distributed to optimize the way in which the watch will run. Now, this one is very obvious as you see it because of the form that Breguet gave this particular hairspring. It can be done in very subtle ways that you won't see if you examine the watch, but it's still there. The silicon has been made stiffer in some parts, more flexible in others, and the spot where the flex starts has been designed into the watch. That is idealized shape, which is very important to performance and chronometric performance. There is another, this is also a slide I had when we talked about tourbillons. There is another element which I haven't really seen people discuss very much. When we talked about tourbillons, I talked about perturbating torques, which take a hairspring that otherwise would have ideal performance and they disturb it. So we lose that ideal, which lays behind the reason in which a tourbillon was invented, the effect of gravity, which is one perturbating torque. So the problem with a hairspring is you can't have the center of gravity be at the center of rotation. You want it in the center of rotation, that would be ideal. That's what Huygens had in mind, as a matter of fact, when he developed the first idea of a hairspring in a watch. So it's the center of gravity is going to be displaced. The amount of perturbating torque from that displacement is going to be a function of two things: the mass and the distance from the center. If the hairspring has a lighter weight, the mass is less. So the amount of perturbating torque is going to be less. That improves positional performance of the watch. An advantage that I haven't seen people discussing very much, but watchmakers know it, and they're quick to point that out when you want to talk about a silicon hairspring. Almost related, again, something that people haven't discussed as much as they should, is what is the response of the hairspring to the impulse that it gets from the escapement. Silicon has an advantage in that its response is more uniform as the amount of impulse diminishes, as the barrel unwinds. So you get better isochronism performance from silicon than you would from a metallic hairspring. Subtle, but it's there. It's an advantage that makes basically another advantage. It makes silicon an incredibly desirable material to have for the hairspring. My third category here of something that nobody talks about, which is aging. Metallic alloys age. We all do, but metal ages as well. Silicon ages much more slowly. So over time, it will perform better. I'm going to ask a question now. We're moving on to copper beryllium wheels. How many of you who have debated qualities of watches, been together with other watch friends, and you're pointing out different things about the watch and some design and some other element or something like that, how many of you talked about the wheels ever in your watch? I don't see a lot of people rushing the stage, but it's possible. I will say that you are in rare company if you've spent time talking about the composition of the wheels. In fact, if you talk to watchmakers, they're obsessed about them. There are really three materials which allay themselves as choices for watchmakers. brass, which is used mostly, I would say at least 90% of the industry uses brass for the wheels. German silver, which is, that alloy, mostly copper, it's got zinc in it as well, is used by some, very rarely though. And copper beryllium. Now, Blancpain uses copper beryllium for its wheels. It is the most expensive of all of these materials. What is the advantage of copper beryllium? Let's look at hardness first. Brass, this is sort of an average figure, 165 Vickers. German silver actually can bracket brass. In some formulations, it's slightly softer, in other formulations, slightly harder. Copper beryllium is 220, and hardened copper beryllium is 380. In Blancpain's case, they use the hardened wheels in sort of the higher stress areas like automatic winding, where the wheels are subjected to more irregular type motions. But a considerable difference, essentially double that of brass. And what does that do? It leads to better wear properties. It also leads to less friction. There is a production element to it, which I didn't put on the slide. When brass wheels are made, if you have a center hole in the wheel, it has to be drilled. When you drill, you create burrs on the backside. No matter what you do, that burr is going to be there. It has to be removed in some way. That process of drilling and burr removal destroys precision. Copper beryllium, the hole can be stamped, which means that hole can be done to a precision of less than 3 microns. Impossible with a brass wheel. And the thing that is the greater the precision for the making of the part, the better the watch will perform. And that becomes very important. It actually illustrates one thing. I'm sure a lot of you have heard of the Geneva seal. It's promoted by many and talked about. It was a very important set of criteria that were developed many years ago, at least a century ago, to try and codify different techniques and so forth that would make a watch run better. One of them involved manual polishing, for example, of pinions. So there are still some Geneva seal companies who follow that rule and manually polish the teeth of pinions. That's not the best way to do it. There are ways when you don't manually polish where you can get the pinion created to an order of magnitude of 2 micron. A tolerance impossible if you watch a lady doing it the other way. So it's a way of saying there are some things you do in a watch. When you look at your watch, you don't know whether that wheel was made to a tolerance for the center hole of 3 microns and whether the pinions were done at 2 microns, but it matters. It matters on how the watch will run and how the watch will run over time. Another illustration, this is a design that Blancpain has for its wheels. It's kind of unique. I think they're the only ones who have this design. In fact, they can be the only ones with this design by design protection. They call it a jante. It gives a little greater stiffness to the wheel as opposed to the traditional spokes. But the other thing that's interesting, this is a Blancpain chronograph here, and you can see the beautiful anglage which shows on the wheel that I have blown up there. The element which you don't appreciate is almost all the wheels come from one place, industry-wide. There is a company called Gollet, which is in Le Brassus in the Vallée du Joux. They are a supplier industry-wide, both for Switzerland and for Germany. Not all the wheels are specified by the purchasers to the same grade. There are some very famous companies who do not buy the highest grade wheel and don't buy the wheels that are finished with a fine anglage finish. So if you want to now start paying more attention to wheels, you can examine them perhaps more closely, and you will see differences with the loop and with close examination. This is just a specification even on how they're going to do the anglage. We're all familiar now with many watches offering longer power reserves based upon having more than one mainspring barrel. Generally speaking, to get longer power reserves, the barrels are connected in a series. The question you have to ask is, how are the barrels engineered? Just putting 3 barrels together to get a long power reserve doesn't necessarily tell you how the watch will run over that stated power reserve. Will the torque curve be relatively flat, or will we have a fall off? How do you make the power curve as flat as possible? And there is a trick to it. The trick is by engineering the force of the springs in the mainspring barrel. The outer barrels have stiffer springs than the barrel that is directly connected to the running train of the watch. The idea is that by having the outer barrels have a stronger spring than the inner barrel, as the inner barrel unwinds, the outer barrels will replenish it because they have a stronger spring. There's even a little bit more to it than that. The inner barrel has a fixed spring like you would have in a manual wind watch. You wind the watch and you get to the end and you can feel that it's fixed. Automatic winding watches have to have a slip spring, right? So because the watch can be wound all the time you're moving your wrist. So when the spring gets fully wound, it has to slip inside the barrel. So the way this has been engineered, the outer barrels have slip springs, the inner barrel has a fixed spring, and they have calibrated the strength of the springs to optimally replenish the innermost barrel. The effect is to get a relatively flat power curve over time. Just hooking 3 barrels together won't get it done. That's the real message here. And that's what you should be interested in when you are thinking of a longer power reserve watch. Has it been engineered in that way to optimize the performance? This is probably something that I think very few people understand: secure calendar construction. So we know this problem. When you have a complicated calendar watch, how do you protect the watch against being inadvertently adjusted when an automatic daily change is taking place? I know a couple of collectors, sophisticated, knowledgeable, lots of great watches, who know better, who have attempted to adjust their watches at the wrong time when the watch is in the middle of an automatic change. They have broken the watch. So what do you do to guard against that kind of mishandling? We all can make mistakes, even people who are quite knowledgeable. So, of course, yeah, read your owner's manual always, run the watch through midnight, set it to 6 a.m. and you'll be safe. But there is also another way. Now, the calendar plate I'm going to focus on is one that is emblematic at Blancpain, which is the classic moon phase with the day and the month in windows, the date with an exterior hand. This is what Blancpain has been doing since the early 1980s, this particular arrangement. It's in the Villeray collection, which is the more classic collection. It is in the sport collection, like the 50 Fathoms or the Bathyscaphe that you see here. Looking now, I'm going to start taking this watch apart for you. So this is now looking at the dial side of the movement, the part that only the watchmaker who built the watch and the watchmaker who services the watch will ever see. We'll go to a diagram, and now you can now get yourself oriented to what we're going to show. We have the day of the week, which is going to rotate counterclockwise. The months rotate clockwise. We have the moon phase. And of course, I can't show you the hand for the date, but that's going to be in the center. Now we're getting a look at the mechanism that underlies the watch once we've taken the disc off. And what I'm going to do is walk you through each one of the indications, and we're going to look at it in two dimensions. The first dimension will be what happens with the automatic change. What happens when you manually set the watch? You have two things you have to look at if you're going to develop a secure mechanism where you won't break it if you are adjusting it at the wrong time. So let's start with the moon phase. The moon phase disc is the disc that you see in yellow. At position E, you have, position F, you have the pusher for manually adjusting the moon phase. The key component for the daily changes is right here, that green disc with the orange knobby disc, which is running along with it. Now that knobby disc is not solid to the green disc. The green disc is a 24-hour wheel. It turns once a day. It carries along with it that mobile that is given some degree of freedom. And that mobile nose, which actually has a tiny roller in it, is what's going to command and accomplish all of the automatic changes except the month. And we'll get to that in a moment. So when, I want to go back. I keep going the wrong way here. There we go. We have this lever, which is now in contact with the nose of the wheel running with the 24-hour wheel. As that nose passes this lever, which is in brown, it is going to depress the lever, which is in contact with one of the teeth of the moon phase disc, which will advance it. So that's the automatic advance. What happens when we do the manual adjustment of the moon phase? As F is pushed, it is going to go along this long lever, and it's going to do two things. One, it's going to come in contact with the automatic changing arm here. As it pushes the automatic changing arm to adjust the moon phase, it's going to be pivoting it away from the nose that would do the automatic change. So two things happen. One, we disconnect from the automatic, and two, we accomplish the change manually. And that's going to be a theme as we go through everywhere except the month. So the day of the week, the same idea. We have that same nose now that is moved further along, coming in contact with the pink arm that you see, which engages with one of the, surprise, 7 teeth of the wheel for the day of the week. The automatic change, when the nose hits that pink arm, that will push the nose in contact with the day of the week wheel, turning it counterclockwise, advancing it by 1 day. When you command a manual change, which is up here at J, the arm will pivot to make the change at one end and pivot away from the automatic 24-hour change. Same idea. We're going to see the same thing with the date, the same operating principle. By the way, this sounds really easy, but it takes the complexity of this calendar and it moves the component number to something approaching a perpetual. So it sounds really easy, but it's much more complicated than if you didn't want to build in this safety feature. So here we have the green grand lever. They call that the grand lever because it's the largest one. Same thing. for the daily change, that same nose will hit the green lever, causing it to turn and move the date 1 tooth, which would be 1 day. When you do a manual change, which would occur by pushing A here, that lever will pivot, hit the pin on the grand lever, which will move the date 1 day, while at the same time pulling that grand lever away from the automatic change. Okay. Things get very different for the date. Now, the date is kind of interesting. So we have a 31-day wheel in the center, which is in yellow, and you'll see a snail cam, which is above it. Now, this is going to be turning clockwise. The month has a lever, which you see in orange, which is normally in contact with this snail cam. And if you follow that lever all the way around, you can see its beak comes up here to a 12-tooth wheel for the month. Actually, having a safety system for the month is probably not required, because the way the month change occurs is when the date advances, this lever, the orange lever, encounters the cliff of the snail, and it has a spring that automatically drops it down. So the change is instantaneous. It's almost impossible to imagine with an instantaneous change how you could intervene with a manual change simultaneously. Probably couldn't. But nonetheless, there is a system to protect. The manual change is made up here by T. It has its own long lever, which can engage with the month wheel. When you push to make the manual change, what it does is it removes a blocking pin up here, which otherwise would hold the automatic date change beak in position over the wheel, which allows that flexible tip, also based on the shape of the gears, which you can see here, to freely pass, let the gear freely pass by it. So you have a double protection, instantaneous, and you allow the automatic changing mechanism to be pushed aside. So what we've done here is looked at what I call hidden figures. I think there hopefully were some things that you hadn't appreciated before, hadn't thought about before, didn't consider to be part of what you valued in a watch, but I hope I've illuminated, expanded your way of thinking to these new things. Thank you.
That's amazing.
Okay.
Brett, could you turn on the mic? All right. Thank you, Jeff. That was amazing. Now we have some time for Q&A. If anyone has a question, please raise your hand. I'll bring the microphone to you. All right, here in the back.
Thank you for that. Very enlightening. Quick question on the last part. Does the complication on the calendar, does that trigger the 30, 31, 28, 29 days? Or is it just pure, just goes to 31?
This particular calendar that I showed you is what they would call a simple calendar. In other words, it is not an annual calendar. It is not a perpetual calendar. So you have to manually adjust when you get to the 30-day months or the 28, 29.
So I've got a question for you, Jeff, and then we'll go up here. So back to the copper beryllium wheels.
Yeah.
You were talking about how copper beryllium is better in the sense that it's harder than brass. So just playing the devil's advocate here, Why not make the wheels out of steel?
Good question, and I don't know the answer. You make the pinions out of steel. What the barriers might be in terms of machining cost and so forth, I can't give you the answer to that.
All right, up here in the front.
By the way, I can actually think of an answer, one answer, which is that in most cases throughout the watch, you have a combination of wheel and pinion, which the watchmaking term is mobile, right? So what they're doing is they're taking a pinion and attaching it to the wheel. So having a slightly softer material for the wheel allows them to actually slam the two together and they hold together. How you do that with the precision so that everything stays flat and so that it's solid and so forth and so on is one of the great arts of making those mobile components. How that would happen in terms of how you would machine it, if everything was steel, I don't know the answer.
I've heard people like FP Jordan, traditional watchmakers, who've stated that they would never use silicone for hairsprings because it can never be repaired. They've used that as being a reason that they don't use silicone as opposed to traditional materials for hairsprings. Is that something that you would comment on? I mean, can traditional hairsprings be repaired if they're stretched or if they're?
Yeah, I mean, yeah, no, you can't repair a traditional hairspring either. If you bend it, it's going to be deformed. So there was a lot of skepticism when silicon came in. Everybody said, the watchmakers will break it. It's going to cause a problem when you do service. At this stage now, there have been so many watches made with silicon hairsprings by so many companies at this point. I mean, it's every Blancpain watch is a silicon hairspring, every Breguet watch is. Patek Philippe has gone that way and so forth, and Rolex too even. So it's industry-wide and thousands and thousands and thousands of watches, and all of the horribles that people talked about don't seem to have come to pass. So whether Francois Paul would say the same thing today, if he had a supplier of hairsprings, I can't speculate.
Any other questions? Yeah, let's go right here to Luca.
I had a question about, are there any other components in a watch that you view being benefited by the use of silicone?
Yes, you see a number of different components that can be used. An escape wheel in silicon. I've seen the whole pallet assembly, the Swiss lever done in silicon. There are a number of watches that have been done that way, particularly at watches that run at higher frequencies. That has been done. Again, the lighter weight becomes important.
More. Let's go right here.
I've heard people talk about the silicone hairspring and that making it anti-magnetic. I haven't heard much conversation about other components of the watch being magnetized. Could you comment on if there's a risk of other parts that are metallic that could potentially make it less accurate, or is it just really the hairspring that's the most critical?
The hairspring is the most vulnerable, the most easily magnetized. And I would say to the extent you've had watches where they have suffered residual magnetism, it's the hairspring that is the most easily demagnetized because it's the most easily magnetized. Yes, other components, if the field is strong enough, can be magnetized and adversely affect the running of the watch. So that's why, generally speaking, it's not recommended to wear your watch in an MRI machine. Okay, but to be honest, that is you have to be in a pretty severe magnetic field before you start affecting the other components.
I have a question. With regards to the magnetism, I actually took my ceramic case to Planet Ocean 2 in MRI, and ran an MRI and had it slam against the machine. But the watch didn't break. The watch was magnetized, but it didn't run fast or slow. So the hairspring does make a difference. And as for, I have a question about the regulation. So in this lecture, you compared the inertial regulation versus the Raquette regulation. And it seems that a lot of the watchmakers, watch brands are still preferring the Raquette over the inertial regulation, because I mean, with the current industry trends, I mean, we see the inertial regulation being more utilized in the Swatch Group brands, Omega, Blancpain, Breguet, and so forth. And Rolex has implemented it with their new series of movements that came out last year. But I haven't seen inertial regulation as often as we prefer it.
I would disagree with that strongly. I have seen, I don't like naming names.
Of
I
course,
can
of
think
course.
of one
Certain
very high-end brand who was using raquettes for a very long time, who transitioned now completely over to inertial. I can also think of another prestige watch brand that has stayed with Raquette. I happen to know that it was done as a matter of cost. I, at this point, don't see any good reason why, at the kinds of prices that we pay for prestige watches, why they wouldn't be inertially regulated now. Just personal opinion.
Makes sense. Thank you.
And I said hidden figures. That is one thing I do look at when I look at a watch. So that's kind of hidden in that we don't talk about it as much as we should, but it's totally obvious if you look at a clear case back with what you have.
Hi, Jeff. Thanks very much for the talk. I have a question about the copper beryllium wheels.
Yeah.
You say they're more expensive. Do you know, can you comment on how much more expensive? Why wouldn't people use them over anything else? Just because it seems like it would, like you're saying, elongate the timeline of the watch.
Don't know the order of magnitude, but it is an issue when you think about how many you have to make and whether you're going to standardize for your collections on brass or whether you'll standardize on copper beryllium. Again, it's something that to me now is something I value very greatly in a watch. I know it's better, and I know why it's better.
There are safety issues. It's toxic. So in the manufacturing environment, there are many more controls over the waste products. So they're collected and try to minimize the possibility of operators inhaling it. It can cause borreliosis.
That's very, very true. Thank you, Jeff. Any other questions here in the audience? All right. Well, let's give Jeff another round of applause.
Thank you, everybody.
All right, everyone. Thank you for coming out tonight, and we'll see you back here in June for the final lecture before our summer break. Thanks, everyone. Have a great night.